Hi, this is Nathan. The next example I want to do is the uniform distribution, where the bounds on the distribution are between 0 and theta, where theta is a unknown parameter. This question is actually deceptively tricky. We cannot use the method that we've used in the last 4, 5, 6 examples on this one. What makes this tricky is that the support for the distribution depends on an unknown parameter. For the last examples, like the normal distribution, right? It has a support from negative infinity to infinity. While Poisson has a support of 0, 1, 2, up to infinity, while exponential has support from 0 to infinity, right? All of these are not dependent on a unknown parameter. Okay, so let's talk about how we would go about solving the uniform problem. The density for each sample is 1 over theta, because it goes from 0 to theta, but only if x is less than theta, right? So it's 0 otherwise. Another way you can write this is that the density for each one is equal to 1 over theta times indicator function that xi is less than theta. The indicator function, if you haven't seen it, will give you 0 if this statement is false, and 1 if it's true. So in our case, this will give us 1 if xi is less than theta and 0 otherwise, which is a nice compact way of writing this support, or what the distribution is for all values of x, right? So then we take the joint PDF, which is equal to the likelihood function, and we have this product from I equals 1 to n of 1 over theta times I xi is less than theta. And now what makes this question different is if we try to take the log likelihood function, it's not actually going to be any simpler for us. So instead of that, we're just going to go with the likelihood function. Writing this, we get 1 over theta to the n, because there's n of them, times I that x1, x2, up to xn are all less than theta. Because if even a single one of them is greater than theta, then we get 0, right? Which is equivalent to the maximum of x1 to xn being less than theta. right? Because if the maximum value of x1 up to xn is less than theta, then clearly all of them must be less than theta. So let's graph this. So we have theta on the x-axis and the likelihood of theta on the y-axis. If theta is less than the max of the xi's, right, then the likelihood is 0, because this will become 0. While if theta is greater than the maximum of the xi's, we will have that this right part will be equal to 1, and this left part will be what determines what the likelihood is. And note that 1 over theta to the n, where theta has to be greater than 0, and n also has to be greater than 0, is monotone decreasing. For theta. So the bigger that theta is, the smaller that 1 over theta to the n is, put another way. So we have something like that for what this will look like. Note that anything to the left of the maximum value of the xi's is equal to 0, and anything to the right is not equal to 0, but it's monotone decreasing. So we can conclude that the maximum value has to be there at the max of xi's. So theta hat MLE is equal to max of the xi's.